eye are open, and you're watching this time in the corner of your display here, and you said, how is all this happening? All concurrently and accurately, right? Have you ever wondered that?
Yes.
To do that, we need hardware. Oh, darn it, we need hardware. So it all starts with this oscillator. Okay, so we have inside of the hardware, we have an oscillator, and believe it or not, they come in various qualities. Some are more accurate than others. But the thing that's really fascinating about oscillators is that they run pretty much at a constant speed. Really, 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 really fast. Okay, so it's out there running in the gigahertz in many cases, right, which is a lot of times per second. All right, so we don't want our CPU, which is probably rated at 256 megahertz, to try and keep pace with the 16 gigahertz oscillator. It would probably fry the thing, right? So what we do is we need to say, oh, I want to count every thousandth or every 10,000th pulse of this oscillator. All right, so what happens is it gets connected to these latches, okay, these flip-flop registers. And what they do is they're going to say 1, 2, 3, 4, 5, 6, 7, 8. So you put enough of these together so that you can skip over every 10,000th pulse, if you will. So that way you can get one clock cycle. Okay? So that's typically how we implement the clock hardware, is some combination of the oscillator with these either D-latch flip-flops or JK flip-flops that we can then just put a bunch of them together, depending upon what clock speed we want to run this thing at, and then just count to that value to get to one clock cycle. So for those of you enterprising techies out there who want to try overclocking their systems, okay, because you read that these hardware manufacturers are putting out these chips that work at 256 megahertz because that's when most of them will work. But that means half of them can work at faster speeds. And my luck is I have one of the ones that can work at faster speeds, right? So you crank this sucker up to run at a faster speed, hopefully not one that is too fast for your CPU and it melts down. And then you're a happy camper with an affordable machine, okay? So yeah, you can do that, you take risks with it, but that's really what you're doing is you're just changing how many of these pulses you're skipping over to be one clock cycle. Why is that important? What does that to do with what I just said we wanted a clock in the system for? Gotta have myself here. Because everything on the board needs to be synchronized. The clock is what's going to synchronize it. The clock is going to be what we're going to use for timers, interrupts. The timer is what we're going to be using for the time of day clock. It's going to be controlling the CPU, right? Wait a minute, I thought the CPU was in control of everything else on this thing, right? Well, it turns out the CPU is a slave to the clock just as every other hardware component is, other than the power. I guess everybody's a slave to the power. So oscillator needs power too. So we have this oscillator. Sometimes we have a battery in there so it can continuously run even when we have removed AC power, which is being converted to DC power. So the oscillator and these things can still run. But we need this to be running so it can synchronize everything. And our good friends in the C department that are amongst us here can tell you what happens when we power up our machine. We first supply power to the hardware itself. The first thing that the hardware has to do is it has to get all of these different components synchronized to a clock cycle so that they all understand that they're on this clock cycle and they're either positive phase or negative phase depending upon the design of that system, so that they know who's on the bus, which of these different components. If we're sharing buses, remember that lecture on Monday? So if we're sharing buses, then we'll know who's doing reads and who's doing writes on that particular cycle. That way all the components are working together instead of total chaos. Which for those of you who are in chaos theory might sound like a good thing, but your CPU will never run with chaos on the board itself. Okay, so we control it all with this oscillator, the clock. So what does the clock do? Well, yeah, we got the time of day we just talked about. We're using that as part of our time quantums, right? So we'll establish a time quantum, and every process is using the same CPU, which is using the same clock, and so they can all run exactly the same amount of time. Now, I will talk about multiple CPU machines for just a second. In multiple CPU machines, they all still use a single clock because all components in the system must be synchronized to a single clock. Accounting data, alarm system call. So if you're using alarms, right, they're going to be notified when the clock reaches a specific time interval. Or specific, you're going to define an interval, and then what you're going to do is register for an event at a specific time based upon that interval that you told it to, so that when the clock reaches that value, it can then raise the alarm so that your process can get notified that your event happened at the time you asked it to. Watchdog timers, profiling monitors, status, all those good things that clocks can do. Okay, so now we think about, all right, I got this clock going on, I've got this operating system, and I have this concept of time, which is days, which is years, months, days, hours, minutes, seconds, right? And sometimes fractions of seconds. So we have that construct that we live with, but I have this single oscillator just going all this time, right? So one of the ways that is popular in the way we do it in Unix and Linux systems is what we do is we maintain an epoch time, okay? Time of day index. And so we will create a 64-bit register, 64-bit word to contain this value. And what we can do with that is we can say, however many ticks since the system was created, not when the operating system started, but when the system was created, I can then calculate, determine year, month, day, minute, hour, minute, second, from that number of ticks since epoch time, okay? And that's how many systems are designed today, especially Unix, Linux systems. Okay, so typically a 64-bit, and then we can further subdivide it for time of day in seconds, number of ticks in the current seconds, and so on, okay? We care about that so we can format this time to be something meaningful like an actual day and time and within the day and all that kind of stuff. But we can also be concerned with things like, well, how long has the system been up since we last booted it? Right? That's always a fun one. Have you ever log into Rohan or uptime? I'll tell you some interesting statistics about the system and its health and numbers of users on it and all that kind of fun stuff. Okay, and it's doing exactly this. It's using epoch time and some other statistics metrics that it's maintaining to tell us some things about the system. Okay, so I keep talking about registering for events, right? So let's talk about that a little bit further. So if I want to register for an event, okay, that means I'm at some time. So in this example here, we're at 4200, okay? So I'm going to say something like, oh, what if I want to have an event go off in 3 seconds or whatever value I want it to be? What I can do is I can take current time plus the time in the future that I want to be notified, and then insert that into my clock's queue. The clock's going to maintain this queue because I'm not going to have an event every second. I'm not going to have an event every minute. I'm not going to have an event every microsecond. I'm going to have events asynchronously, just totally independently and random, almost random if you will, in the future that I want to register for. So what will happen is I'll take and I'll figure out, well, what time do I want to be notified? 4200 plus when I want to be notified, 3. I'm sorry, 3 is the next signal. Disregard that. So if I want to schedule for something, I don't know, 10 seconds in the future, then I would take 4200 plus 10, and then I would look in the queue and see who's furthest out, and I'd insert myself there into the list. And so what this will do then is it'll say, oh, the next event in the future is 3 seconds from now, so it will just put that into this next signal event. So what I can do is, instead of comparing my current time with some linked list, I can have this special piece of hardware here doing the comparison for me, so that when 4203 is generated, I can then send this, dispatch this event and process it. And then I would put 4 in here, so at 4204, I would schedule that event, and so on. Okay? So I have this linked list, which allows me to insert, because I may have something, bad example, I may have something that wants to be 5 seconds in the future. And so I might need to insert it here, which is why I'm using the linked list structure. Yes?
So the data is ordered, right?
Yes?
Well, why is there a 2 and 1 after 6?
2 seconds later, 1 second later.
Oh, so it's relative to.
Relative to that, right. When I go to insert the list, that's all I'm going to do is determine the relative, because I want to just slam that value into this next branch. Next to it, rather. Okay. Other questions on the clock? Clock's kind of a big deal. Okay. Then there's these soft timers. Okay? So soft timers are not built into the hardware, but we're going to use hardware, of course, to implement them with. But we're going to have code running to process these, right? And some examples of those are in some cases, some systems calls. We have a timer system call, we have a time system call, and a couple of others that allow us to construct our timers, and what they will do is they have some additional processing that they will do to make an easy system call API that you can use to create an event to happen in the future. Okay, so I might build a system call to actually put an event onto the queue. That's fine. TLB misses are soft timers, but they're going to be implemented in PROM. In other words, the kernel is going to run and take advantage of some stuff that the hardware manufacturer made, but you can still trap for your TLB misses and instead build your own kernel code to process it instead. Okay, so you can implement your own version of how to deal with TLB misses simply by trapping for that event. Page faults. There's a lot of work going on in a page fault, right? So it's really a soft timer. It's not something built hard into the hardware. So we'll process those. I/O interrupts, the same thing. We just talked about interrupt handler routines, right? So those are soft timers. And 5 is one of the most interesting things I've ever seen an operating system author to actually use. CPU going idle. Most CPUs never go idle. There's no such thing as an idle CPU. Even the CPUs that go idle, they're not really idle. They're just sitting there looping on load A register, load accumulator register, load accumulator register with 0 over and over again. CPUs are slave to the clock's pulsing, causing the CPU to fetch an instruction and perform an instruction. That's the life of a CPU. Remember chapter 1? Yeah, life of CPU, fetch, execute, fetch, execute, fetch, execute. So what a CPU does? CPUs don't go idle. Well, back in the 60s, they actually had CPUs that did go idle. They even had a switch. They had these hardware consoles that you would operate them from, and a lot of them had these banks of switches that you can do different things to make it go through the sequences. One of them was actually a halt switch, which actually made the CPU stop. But we haven't had one of those computers since '68, so I don't know why we're still talking about this CPU idle nonsense. It's like, no, haven't seen one of them in a long time. The life of a CPU is simple, straightforward, and just like we talked about. It's by a long-winded way of saying not testable. Okay, there's a couple of sort of catch-all things that falls into this chapter. It is the appropriate place because this is still I/O, but it's a little bit different context than what we've been talking about. It's still part of the operating system, very much part of the operating system, but now we're talking how we're interpreting bytes, okay? And the problem that we have with, that we're talking about here, that we're using this example to illustrate, is the fact that I have the need for keyboard and video input and output, right? Which is interactive. Well, at least the keyboard's interactive. But it's interactive based upon what the user sees on the output device, right? So they're going to have some output on the output device, and they're going to have some input from the input device, the keyboard. The problem is that some of the things you input on the keyboard is data, but some of the things that you input on the keyboard are control signals. So the simplest of examples, many of you are familiar with Control C and Control D, right? Okay, so that's an excellent example because those are control signals. How do we know they're control signals? Because ASCII for the combination Control C and Control D gets mapped to ASCII code that can be interpreted as very specific control signals. Okay, so what we do for that particular input device, if the input device is a keyboard, we are translating those bytes as we read them to determine if one of them is actually a signal versus data. Okay, so that means we have to define those things, right? And so what you see here is a table of some basic I/O interpretation that you can set up and you can set. Now, for those of you, getting ahead of myself, okay, let's finish this. Okay, so these are the characters and the POSIX names for some of these control sequences. Since we talked about Control C, Control D, here's Control D here. That combination gets mapped to ASCII, EOF, or End-of-File. Okay, which when you are running your terminal, coming through your terminal, means interrupt, right? Well, interrupt can also get mapped to this. Okay, and then you have these other control lines as well. So if you go to, here's what I started to say. If you go to your terminal, and you type, it will tell you your settings. And you can also change your settings.
What's this, STTY?
STTY.
Okay, that's what I thought.
If you do that, it will tell you what control signals are mapped to your particular terminal and how they're interpreted. The problem is this is just one layer. This is the operating system side. Okay, so when you log into the operating system from your host workstation or laptop, you're going through your own terminal settings to get to the host computer, the remote host computer, getting into your shell, and it's going to tell you its terminal I/O settings. Okay, and sometimes they get mismatched. So if you've logged in before and you've hit the backspace key, and instead of backspacing and rubbing out the character, it instead gave you some wild sequence of characters and you got all mad at it, it's because you have a mismatch between your control character settings on your local machine versus the control settings on your remote host computer. Yes.
Can you change that?
Yes.
No.
Just STY controls DEL and then the sequence that you want.
Okay, because Rohan, oh my. Well, because the default C shell, like you need to use like X cores, you need the X11 for you. But like if you're using C shell, it just does not play at all. But if you change it to Bash, you can log in through like, your normal shell. You just can't launch into it, which is whatever you just use VI. But like backspace does not work on Rohan, and it
This
pisses
does.
me off.
This does.
No,
So-
no, it's not. You have to go back, you can press X for delete.
do this. When you're logging into Rohan, when you first log into Rohan, you're really eager to do it, and you start clicking through everything, right? One of the prompts that you probably are clicking through is its request for you to tell it what type of terminal you are connecting from. Okay, and you have many choices here. VT100 is very common. ANSI is another common one. Depending upon what terminal type you enter when you're clicking to get into your login session, it's going to set a set of default settings for your term IO. If you pick the wrong one, they're going to be messed up.
If you SSH, you do it.
Same thing. SSH is going to do the same thing. That's just doing a remote login or a remote. It's using SSH protocol, but using a secure version of it. But it's still doing the same thing. When you start your process in Rohan, it's going to create a new process. It's going to exec overlay it with your shell. And one of the things your shell is going to do is ask you what type of terminal are you logging in from.
Well, I mean, okay. I mean,
It
it
won't-
doesn't automatically, you don't choose this.
It prompts you for it, unless you set up your,
Like CSH?
yeah.
You change shell?
No, not to change, no, your shell resource, your resource file. Okay, your .file. So if you change your .file to do these mappings for you, then it's not gonna prompt you. But if you don't change them, then you've got to enter it.
This is term unknown. I
Yes,
used
if
to
it
have
says
to-
unknown, then you just change it, because it gives you the option to change it.
Yeah, if you do CHSH and you do bash.
You do change shell too, but at normal login, it's gonna ask you that anyway, unless you configure your .file.
Interesting.
Is it yours? So those are ways that you can get the mappings for you. Of course, that's assuming you're logging in from the same machine each time, right?
So, yeah, of course.
Of course. So backspaces and deletes are the most common, but there's other term IO settings as well. You do STY, A to see them, you can set them, you can configure them in your .dot files. A lot of applications, if you're using applications to do your SSHN with, or SFTP and such, they also have some mappings that you can change, and it'll automatically send those to the shell when it logs in. That's what it's doing. Okay. Oh, is that it? Yep, that was it for the chapter. Any questions on chapter 5?
There's a lot of them.
Good stuff, right?
Interesting.
Okay. Shall we get started on chapter 6? Everybody laughs. I go back to somewhere I had. Oh, here it is. Syllabus. I go to here. Okay. We said we were going to go halfway into Monday's lecture with chapter 5, but we managed to finish it up tonight. That means we have chapter 6. So we might get all the way through chapter 6 on Monday, but it might bleed over into Wednesday. But if we start in 6 now, I know we'll finish 6 on Monday.
Flip a coin.
It's fine.
Six is pretty short. No, it's a good
Yeah,
chapter.
it's pretty short, but there's a couple parts of it that are going to take a while to walk us through.
At the same time on Monday.
Yeah, all right, we'll do it Monday.
Yeah.